Hello everyone, welcome to this new virtual tour of the European Southern Observatory, or ESO is acronym. My name is Hector Salas, and together with the producer Farid Char, we will be your guides through this virtual experience. So before we start, allow me to introduce myself. As I said, my name is Hector Salas, and I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mainly with topics related to the circumgalactic medium, that is the environment that immediately surrounds the galaxies. And I have been a part of the guys of Paranal Observatory since 2019. I started while I was doing my master's degree in the University of Antofagasta. And I'm not alone today, I'm with Farid, who is going to be our producer. Farid, how are you today?
Hello, Hector. How are you? And welcome everyone to this virtual tour um, uh, for the ESO Paranal Observatory. From my side, my name is Farid Char. I have been working as a tourist guide for Paranal Observatory for more than 10 years. And in my case, uh, I have been working with an astronomy center in the University of Antofagasta. So I am very familiar with astronomy outreach and education. And one of my main hobbies is astrophotography, telescope observations, and so on. So I will be in charge of collecting your questions or comments. So later we will have some time for answering those questions in some portions of this tour. So please go ahead, Hector.
Thank you, Farid. So as Farid mentioned, you can send us all your questions, your comments, your greetings, and we'll have some instance during the tour to try to answer any doubt that you might have. So before we start, let's talk about ESO, the European Southern Observatory. So we will show on the screen an image displaying the 16 member state of ESO that you can see there. So we have Denmark, the Netherlands, the United Kingdom, Ireland, Belgium, France, Portugal, and Spain. Sweden, Finland, Germany, Poland, Czech Republic, Austria, Switzerland, and Italy. And as you can see, there are a couple of non-European countries here on the screen. We have Australia on one side that joined us a few years ago as a strategic partner. And on the other side, we have Chile. Chile is the host country. All the telescopes and observatories that ESO handles are located in Chile. During the 60s, ESO was in a mission to try to find out the best place to observe the southern sky. And at the same time, Chile was trying to attract human capital to the country. So they come to an agreement in which Chile will hand up the land and ESO will build these observatories. And they look for the best places to do this. There are three observational sites of ESO in Chile, and we will show them on an image. So the first one was La Silla Observatory. That's when we started in the 60s. And in La Silla Observatory, the main telescopes that we have there are the ESO 3.6 meter telescope, or 360 as somebody's called, and the NTT. And the ESO 3.6 meter is equipped with an instrument called HARPS that is specialized in detecting exoplanets. So these are planets that orbit stars that are not our sun. Towards the north, we have the Changnan Tor Plateau. And then we have Apex and ALMA. And in the case of ALMA, this is not just controlled by ESO, but it's a consortium with ESO, the US, and some Asia Pacific countries. So we are just one of the members of this collaboration. And then in the same region of Antofagasta, towards the coast, we have Paranal, and we also have Armazones. So in Armazones is where the ELT, the extremely large telescope, is being constructed. This is going to be the largest telescope ever built. And very close to the side of Armazones Mountain, is Paranal Mountain, which is the place we are going to visit today. Their main telescopes are the BLT, the Very Large Telescope. We also have there the BST and VISTA telescopes and the BLTI, the interferometry array for the BLT. And in the area between the ELT and Paranal, within Amazonas and Paranal, there is being built there the CTS South. This is an array of telescopes that is going to detect gamma rays. So this gives you a brief idea of the different observational sites that ESO has in Chile. So now we're going to virtually travel to the Paranal Observatory. And in the meantime, let me tell you that the mission of ESO is to design, build, and operate astronomical facilities so we can expand our knowledge in astronomy and the collaboration in the science of astronomy. So right now we are virtually flying over the Atacama Desert, the driest desert in the world. Overhead in the distance, far distance, we can see the summit of Paranal mountain. This mountain has 2,400 meters above the sea level and is the house of the Paranal Observatory. Now, we are just 12 kilometers in a straight line from the coast here. So you may wondering, if we're so close to the Pacific Ocean, why this place is so desertic? And also, where is the Pacific Ocean? Can we see it in this image? And on the background, you can see a sea of clouds, a very hazy sea of clouds. Well, the Pacific Ocean is directly below those clouds. So where are the clouds in a place for astronomical observations? Well, this is an effect of the Humboldt current. This is a cold mass of waters that comes from the Antarctic and goes through the coast of Chile and Peru, and it produces a phenomenon known as thermal inversion. And basically what this does is that all the humidity and the clouds they form below 1000 meters above the sea level and they stay there. They cannot enter towards the land because they are stopped by the Chilean coast mountain range, which has mountains that are above 2000 meters at this point, and Paranal Mountain is one of those. Now, we also have another natural barrier in this region that helps make this place the most excellent place for astronomical observations from Earth. Toward the east, we have the Andes, with mountains that reach over 6,000 meters at this place. And they stop all the clouds and bad weather coming from Argentina and Bolivia. The result is this very dry desert, driest desert in the world, that had an average over 300 clear nights per year. This is a very calm and transparent atmosphere, an ideal place to observe the night sky. Now, we're going to change our view to see the mountain closer. And in the meantime, I can tell you that Paranal in the Quechua language means whirlwind. This is probably a reference to the whirlpool that sometimes form in the desert. But as I said, the air here is usually very calm. And we can see in this close-up that this is not a normal mountain. The top has been flattened, there is a road, and there are some very impressive telescopes that have been built there. So we're going to put ourselves on the main platform of the observatory, and we are going to look around a little bit. So here we are at the main platform. First, let's just look a bit around. So we are looking now toward the Pacific Ocean that's below this sea of clouds that they never come over to the top of the mountain. If we switch our view, we can see the beautiful landscape of the Atacama Desert. We are facing now the south, and now we are looking towards the east. Over here you can see in the distance the Andes, and this arrow here is marking the position of a volcano, the Yaco volcano, and that is actually on the border between Chile and Argentina. Chile is a very long but very thin country. And over here we have the site for Amazonas, which is very close. Now, the main star of the Paranal Observatory is the VLT, the Very Large Telescope. But this is not a single telescope. It's a group of four very big telescopes that we can see here on the screen. So we have here the UT1, where UT stands for Unit Telescope. Then we have UT2, UT3, and UT4. And as you can see, they are very big. Here at the distance, we can see a truck and a person walking. So that gives you an idea how large they are. Now, each of them has a telescope with a main mirror that is 8.2 meters in diameter. Now, in addition to the UTs, we also have other telescopes here. So we have these ones. These are the auxiliary telescopes, or AT. Each one of them has a primary mirror that is 1.8 meters in diameter. So at about the height of a tall person. There are four of them. We have one over here, another one over here, then at the Earth, and a fourth. And as you can see, they are on top of tracks, and that is because they can be moved. The 80s, they work together using the technique of interferometry. And we have a small video, a small animation to explain this better. So when we're doing interferometry, what we do is that we point the different telescopes to the same object in the sky. So we're looking at the same galaxy of the same planet or whatever target of interest we're doing. And we're generating a virtual mirror that is equivalent to an actual mirror of the of a diameter equal to the separation between the telescope, the largest separation, what we call the baseline. This virtual mirror allows to get better resolution, and this is the ability to differentiate two objects in the sky. So if two stars are very close and we have low resolution, we will see them as a single star. But if we have high resolution, we can differentiate between them. Now, if we want to see things that are fainter, we still need to collect a larger amount of light, and that does require us to build larger telescopes. And that is one of the reasons why we're not only using interferometry, just building a large number of small telescopes, because we also lose some light. And as you can see in the animation that is on screen, the light is collected in a central building. The light, this is not a post-processing that we do when we do interferometry. The light is sent to underground tunnels using mirrors to the interferometry building. This is completely analog. Okay, let's go back to the main platform. And there we are. Okay, so the UTs, they can also work doing interferometry, but they can also work independently of each other. And as I mentioned, they have a primary mirror that is 8.2 meters in diameter, and they are the same on the inside, but they have different instruments. They have a space for three different instruments or three different cameras. And that is the only difference between them. And we're only going to enter to one of them, to UT3. Now, as the telescope, we're also given a name in the Mapudungun language. This is the language of the Mapuche people, which are the natives of the southern part of Chile. And in that language, we have Antu, which means the sun. That's UT1. Then for UT2, we have Cueyen, which means the moon. Then UT3 is Melipal, which means something like four stars, and is a reference to the Southern Cross constellation. And finally, we have UT4 Jepun, which means something like the evening star, and is a reference to the planet Venus that is very bright either on the evening or before sunrise. Now, we don't have time to go into each one of them, but as I mentioned, they are the same on the inside. And now we're going to go inside UT3 or Melipal. So here we are inside the telescope. We're in what would be the fourth floor of the enclosure. And here we can see some people doing maintenance to the telescope during the day. And this gives us an idea of how large everything is here. Now, the main mirror is over here. And as you can see, this is not a segmented mirror made of many different pieces. This is a monolithic mirror made out of a single piece. This is made out of a special material called Cerodur, which is a mix of glass and ceramics. It's 8.2 meters in diameter, but only 16 centimeters in thickness. And the layer that gives the reflectivity is a very thin layer, and I'm talking about nanometers, of aluminum. Now, let's switch a bit and let's look at this mirror from below. So here we're seeing at these white cell structures that supports the mirror. Now, this mirror is very heavy. This mirror plus this white supporting structure weighs 22 tons. Now, if this mirror were to be made of the same material of a normal mirror like the one you have in your houses, when you point to the sky and the mirror is tilted, the stress due to its own weight will be so big that will cause it to break. So people at ESO have to come up with a solution. And one solution was to have a much thicker, much heavier mirror, but that is not ideal. So the solution that they found was to use this material called Silodur that has a certain flexibility, so it doesn't break. But that means that the shape of the mirror is going to be changing, and that's not good if you want to have consistently good observations. So the solution was the technology of active optics. And as you can see here, there are some little gray boxes. These are the actuators. There are over 100 of them here, and they are basically pistons. They can push or they can pull. So during an observation night, there is a system that is constantly measuring the curvature of the mirror. This is a concave mirror. And the actuators are actively correcting the curvature so it always remains the same. So we can always have the same quality in our observations. This technology is one of the technologies that has made Paranal Observatory one of the most advanced in the world. Okay, so let's go back up. Now, how does this big telescope moves? Well, this telescope has two motions. So on the one side, we have this blue part of the telescope that is the mount of the telescope. And this whole part here can be tilted on this mount. That's one of the two motions that we have. The other one is a rotation. As you can see, this part of the floor is separated from the rest, and this entire segment can rotate in 360 degrees. So combining this movement of rotation with an inclination, we can point at any place on the sky. But before we do that, we need to open the enclosure. And we can see over here, this part over here that extends sort of in an L shape, that is the part that opens to the sides. And we have a small animation that shows this, so we can have a better idea of how this works at night. Now, as you can see, the enclosure is open, and this is way more exaggerated. The enclosure doesn't float on the air on the side of the telescope. This is just to show it better. Now, the light is going to come from the sky, it's going to hit the primary mirror that is concave, then goes to the secondary mirror on top, which is a convex mirror, and then it's going to go to a third mirror that is a flat mirror. And this third mirror can send the light either to the right or to the left, or can let it go straight down. And that way we can choose which of the three instruments we can use, which here are represented as a red, blue, and green boxes. So if we go back to the platform now here we have one of the instruments is over here. In this case, it's called BIMOS. There is another instrument on the other side that we cannot see, and below here we have the third instrument, Symphony. We can only use one of them at a time. Now, I already showed you the primary mirror. The secondary mirror you can see in here on top, and the third mirror is at the center of the telescope. We cannot really see it too well, but to be somewhere over here. Now, you have an idea of what this telescope is. And now, during at night, there is no one here. Everybody is working from the control room because all the lights here they need to be off because they can disturb the observations. So at night, nobody's here. But during the day, some engineers and people will be doing some maintenance to make sure that everything is perfect for the night of observations. So our next stop is going to be the control room, where the astronomers work at night. But before we go there, let's see if we have some questions or comments from our viewers. Farid?
Yes, Hector, we have some greetings. For example, from Snowy, from Denmark, and also have someone from USA. And this person is actually asking, how do we know the composition of exoplanets?
That is a very interesting question. So there are different ways of trying to get to know the composition of an exoplanet. So uh, one thing that we can do is check how much light is reflected. This is what we call the albedo. And this gives us an idea. For example, if there was a completely icy planet like one of the moons of Jupiter, like Europa, this would reflect a large amount of light. So we have a very high albedo. And in the case, for example, of Pluto, we have more rock and ice, so it's not that there are part that reflects less light, part that reflects more light. That's one thing that we can do, but that's not that much informative altogether. Another thing that we can try to take into consideration is the mass of the planet and try to get an idea of the density of the planet. And that gives us an idea if the planet has an internal rocky core or not. But probably the one that is most interesting is try to find out the components of the atmosphere of an exoplanet. And to do that, we wait for what we call a transit. And this is basically like an eclipse. The planet passes in front of its parent star. Now, part of the light that is going to arrive to our telescope is going to go through this atmosphere, so we can try to identify the components of this atmosphere. And we can look for signatures of things like water vapor, oxygen, carbon dioxide, methane, which by themselves they don't tell us that much, but together they could be an indicator of life because those components together on Earth are an indicator of life. Like you can have methane from a volcano, plus but methane plus carbon dioxide plus oxygen plus other things that could indicate the possibility of life. So and that gives us a lot of information. So we can try to see the light that goes to the atmosphere. We can try to see for a class of our more rocky planets how much light is reflected or not. And we can try to get measurements based on the gravitational effects of the mass of a planet and trying to, given its size, then its density. And thus give us a bit of one idea of the internal structure. So those are three ways that we can try to know the composition of a different planet.
Okay, thank you, Hector. We have one more question from Robert Homunculus. Will the ELT be able to resolve the surfaces of trans-Neptunian objects?
That's a good question. I don't know the numbers at this point. It would also would depend a bit on which trans-Neptunian objects, because it will not be the same to try to observe, let's say, Pluto or Charon or with one of the smaller ones. For some of them, my best guess it will be that definitely yes. I don't know, Farid, if you have some actual data on this.
Not really, but my information is that the ELT will be able to determine things that are so specific, like the composition, the chemical composition of the atmosphere of an exoplanet. So that is probably something that will be possible in the future. But to resolve the surface, I think my guess is that this is something a little bit out of reach yet. But still, if we are able to resolve things like uh, I don't know, a better resolution of something that is more far away than Neptune, yeah, maybe it would be useful. For example, for the dwarf planets, it would be nice. But as far as I know, they are very small objects. They are very far away. So I don't know. Maybe something for maybe some other estimation in the future can determine that.
All right. Any more questions before we
Yeah,
continue?
we have one last question for now. This is from Dimitrios Roisis from Greece. He's asking just a question about, he's asking for a suggestion about for a beginner astronomer having a small telescope. I don't know if this question is about objects to observe. But maybe I can give an input on this. Uh, I suppose if this person is right now in Greece, is in the northern hemisphere, so we are in the southern hemisphere, so the objects will not be all the same. Okay, but we have some objects that can be observed by from both hemispheres. For example, the Orion constellation, uh, um, Scorpius constellation. So basically, people with a small telescope can observe the more popular constellations and try to observe some deep sky objects such as nebulas or open clusters, globular clusters. And Orion and Scorpius are very good choices. And in Paranal, for example, we can observe those things. And of course, we can get a lot of details on that. But of course, with the small telescopes, you can try to observe uh, those popular objects. And I recommend to, I don't know, maybe look at something that is called the Messier catalog. Is a catalog of 110 objects, and most of them are visible with even small telescopes. So maybe you can try with that. Yeah. Okay, so thank you, Hector. We are going to continue now, and later we will have some time for more questions. Okay, thank you.
Okay, thank you. Okay, so our next stop is going to be the control room. So here we are in the main platform, and the control building is this one right here that is on this side. So here we are seeing it from a different angle. And in this building, in addition to the control rooms, we also have some offices for the people that work in logistics at the observatory or the engineering departments. But what we're interested in right now is how do we control the telescopes. Now, as you can see, there are a lot of computers and screens, and this is divided into different sections. So over here, you can see there's a sign that says UT4. So this part over here is just to control the UT4 telescope. On the other side, we have here for UT3, where the telescope that we were just visiting. If we advance through this room, we also have the spaces for UT1 and for the UT2. And we're going to stay inside this area for now. Now, you may be thinking, wow, why so many screens? How many people work here at night? And the answer is during a normal observation night, there's only going to be two people working here. There's going to be one astronomer and a telescope operator. So these telescopes, they are very high tech and very expensive, so they don't trust astronomers to handle them. There is the job of the telescope operators. They handle the telescopes. You can think of this as a pilot or an co-pilot in a rally car or an airplane. So the telescope operator, he's the pilot. He's handling the machine. And the astronomer, he's the co-pilot. He has the route. He oversees the science. Now, if you only have two people working here at night, why so many computers? Why so many screens? Well, you have to remember that each telescope has three different instruments, and we're going to want to have a dedicated computer for each one of them. We're also going to need screens giving us information about the weather conditions. If the conditions for go wrong, we might need to stop observing for the night. And they could be wrong because it becomes cloudy or because there is wind that is of too high speed. But that usually is not a problem. We have over 300 clear nights per year which we can observe from during the whole night. Now, so who can use this observatory? Well, astronomers from every country in the world can use it, but they need to apply. There are a couple of instances in the year in which astronomers have to send their observation proposals. And I believe this actually is going to be changed to a yearly submission of proposals. And the astronomers, they have to send a very detailed proposals in which they have to say which objects they want to study, what is the scientific rationale behind this study, has this object been observed with any other telescope before, how far away is the moon need to be for the observations to be useful, etc., etc. Very well detailed, and is highly competitive. Paranal Observatory receives 8 or 7 times more proposals that we actually have time to assign during a year. Now, most of the observations here are done in what is called the service mode. In the service mode, the astronomer do not travel to the observatory, but they give their instructions to an astronomer from the observatory staff, and they supervise the observations for them. In the case of the visitor mode, in that case, the astronomer gets to travel here, but that is the minority. Now, once the observations have been made, they are private for the astronomer that sent the proposal and his team for a period of about 1 year. They have this time to do their science. After that, everything is made public in a website where all the observations are eventually uploaded. So this gave us an idea of how the science works here, but what are the scientific results? And to show this, we have a small video that will tell you not only the discoveries made with Paranal Observatory, but with all the different observatories for ESO. So this video will show you the top 10 of the scientific discoveries. And I hope you enjoy it. And sorry if we can put the video.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at Lucia was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Well, that was the top 10 discoveries achieved through ESO telescopes and its scientific staff. Truly amazing, aren't they? But we have an extra result, sort of a bonus to that. A team of astronomers captured the first image of a supermassive black hole. Please take a look. The Event Horizon Telescope, EST, an array of 8 ground-based telescopes distributed throughout the planet, coordinated by an international collaboration, achieved the first direct visual evidence of a supermassive black hole and its shadow. This image revealed the black hole at the center of Messier 87, a massive galaxy in the nearby Virgo galaxy cluster. This black hole is 55 million light-years away from Earth, and it has a mass of 6.5 billion times that of the Sun. And this image is a couple of years older at this point, but still a very impressive discovery. Now, we're going to go back to the main platform, and we're going to show you something that you can only see in this virtual tour: the night sky at Paranal Observatory. So we can only show you this through this power of this virtual experience, because at night the astronomers and everybody at the observatory is working to have scientific observations, so nobody can be here at night. So we're going to start by showing probably the most recognizable constellation in the night sky. Here we have the constellation of Orion, the Hunter. So in the Greek mythology, at least in the version that I know, Orion was the best hunter of his generation, and he committed the error of trying to hunt a deer that was sacred to Artemis. To punish him, the goddess sent them to the sky, where he was required to fight with all the different animals that he has hunted during his lifetime. And that is why he's close to the lion, the scorpion, and all the other animal constellations. So here we have Orion's belt, or that is known in Latin America as the Three Marys. Over here we have Orion's Nebula, which is a star-forming region. And here we can see in a very bright orange color, Betelgeuse, the brightest star in Orion, which may go off as a supernova in the next hundred of years or so. Nobody knows when. Now, very close to Orion is the Canis Majoris constellation, and also the Canis Minoris. These are the two hunting dogs that accompany Orion. And this is Sirio, the brightest star in the Canis Majoris constellation, and also the brightest star in the night sky. Now, if we go down from Orion, over here we have Taurus, the bull. These are the horns of Taurus. This is Aldebaran, the brightest star in the Taurus constellation. And closer to the horizon, we have here the Pleiades, an open star cluster. A very beautiful object to observe. So for our viewer that was asking about some objects he can maybe observe with a telescope, the constellation is a very good candidate to observe. Now, one of the advantages to have an astronomical observatory in the southern hemisphere, it is that unlike in the northern hemisphere, we can actually see the totality of the Milky Way. And we have it over here. So, our galaxy, the Milky Way. Now, very close to the Milky Way, we have these two, like, sort of fuzzy clouds nearby. These are the Magellanic Clouds. So they owe the name to Ferdinand of Magallanes, who did a trip around the world in his ship, and he was one of the first persons to describe them. Now, these are not actually clouds, these are satellite galaxies of our Milky Way. So we have the big Magellanic Cloud over here, and the small Magellanic Clouds. These are irregular galaxies. So they are not spiral galaxies like our Milky Way is believed to be, and they are also not elliptical. They have an irregular shape. And an interesting thing is that you can use them to try to identify the southern celestial pole. Or like in the northern sky, where there is a very bright northern star, there is no southern star that is very bright and easily recognizable here. But one thing that we can do to try to find the southern direction is to build a triangle using the two Magellanic Clouds. So we extend the triangle towards the direction of the Milky Way, and over here, this is the southern celestial pole, directly downwards, the southern cardinal direction. That's one method that we can use. There is a second one using the Southern Cross. So the Southern Cross constellation is this one over here, the smallest of the constellations. And what we do is we take the large stick of the Southern Cross and we extend it 1, 2, 3, 3.5, some people say 4 times, and we get to the southern celestial pole. So with these two methods, you can find your way in the southern hemispheres. Now, to finalize our view of the southern sky at the observatory, we are going to tell you a little bit of the cosmovision that the natives of this area used to have. And to them, the Milky Way was a river. So this is a river, and different animals, they come to drink in this river. But we don't create the shape of the animals using the stars. We create the shape of them using these darker regions, which are places in which there's a lot of dust and material that obscure or view of the star that are behind them. So for example, we can find here a llama. So we have here the neck of the llama, then we have the snout, the eye, we have the ears, and during the different time of the year, we can also see parts of the body of the llama. And we can also find some birds and other animals. Now, so with that, we are going to go back to the day, and I hope you enjoyed this beautiful view of the southern skies. So let's go back to the daytime, and we're going to go to our final stop in this virtual tour, and that is the base camp of the observatory. So we're going to go down a little bit, And here we are in the base camp. Now this is a mini city in itself. We have everything here that we need to have the observatory up and running. So we have some workshops and some support buildings, some building where new material, new pieces for the telescopes are created, some maintenance can be done. But we also have things like a gym when people can do exercise. We have living quarters, we have an infirmary, and so on. And we're going to head towards the Residencia. This is sometimes called the hotel of the observatory. This is where the astronomers that are observing here they stay. And this looks like we're going to go underground, but we're not. The building is actually constructed on the side of the mountain. Now, before we go inside, let's first take a good look at the landscape here outside. We have a very beautiful desert landscape, but it can be a bit monotonous. It's different shades of gray and brown. And I want you to keep that in mind because what we're going to see inside is completely different. Here we have a very large tropical garden. So why do we have this tropical garden here? Well, this pool that we have here is not just so people can bathe in them and exercise, which they can do, but it's also to have a higher humidity inside this building. Remember, the Atacama Desert is very dry, the driest desert in the world, and that is not good for your skin and for breathing all that much. So, having here a larger humidity and this garden helps the people that stay here. And the people that work here, they stay here in shifts. They stay maybe a week here and then a week at home. Now, this thing at the center, this is a curtain, and this thing expands at night. And unlike a curtain that like you usually have in your house that is to prevent the light from outside coming in, the idea of this curtain is to prevent the light from inside to go out. That way we can turn on the lights inside the building without them disturbing the astronomical observations. Now, this building has 108 rooms. They are located towards this side. Over here we have the reception. It also has a library, a game room, and over here we have the cafeteria when people can have lunch and breakfast and dinner. And with this, we are reaching the end of our tour. But let's see if we have some more questions before we say it over, Vice.
Hello, hello, Hector. Well, no, we don't have more questions so far. Maybe we can talk a little bit about how to visit Paranal Observatory. Is it possible to visit this observatory?
That is a very good question. And yes, everybody can visit the observatories that happen to be in the area. Now, the visits are open to the public only on the Saturdays, every Saturday of the year. And there are two schedules, one in the morning at 10 a.m. and the other one in the afternoon at 2 p.m. This is completely free, but you need to register it in a website. And you need to arrive to the observatory by your own means. There is no bus that bring you here, so you have to have your own card or something. But as I said, it's completely free, and anyone can do it. I highly recommend it. You will see most of the things that we see, but you will see them in person. And in addition, you can also go to La Silla Observatory. We also have a visit for that observatory as well.
Okay, thank you very much, Hector. Maybe some last thing to mention about the observatory, because this is a common question from the visitors there. What happens when we have an earthquake? We have some kind of protection or something, because Chile is a seismic country, right?
Yeah, that's a good question. So, like every building in Chile, they have to adhere to a seismic code to ensure the safety of everybody in the case of a big earthquake, and the observatory is no exception. Now, we do have an additional features that are designed to protect the mirrors of the telescope. So there is a sort of like an airbag that opens in case of a very large earthquake, which I believe hasn't been the case so far, that will prevent the mirror to hit the sides of the telescope. But so far there has been no problem, and just a reminder, there are no replacements for the mirrors that we have in this observatory. So if one of them were to break, we will lose one telescope. So we have to ensure that that doesn't happen. Now, something that might happen with some lesser earthquakes is that we might need to do some recalibrations of things, especially if we want to do something with high precision. So every time after a earthquake below a given magnitude, some tests are going to be run, some calibrations are going to be made. But I don't believe which one was the largest earthquake that we felt so far. Was 7 in Antofagasta?
I have in my memory an earthquake of about 7, but not in Antofagasta. I think in the near Tocopilla or something. 7.7, but I really cannot recall right now. But yeah, essentially the observatory will be fine even with an earthquake of 8 magnitude with the epicenter in Antofagasta. Yeah. Okay, so thank you very much, Hector. So this is one of the typical questions in Paranal when we have the people coming there, and I think we are in conditions to finish. So
Okay.
please.
Well, in that case, first, let me tell you that we have these virtual tours every Saturday, and we're alternating between La Silla Observatory and Paranal Observatory, and also we're switching between Spanish and English. So please keep an eye on our social networks to see when the next tour is going to be, which observatory and which language. And please share this with anyone you know that might be interested. And also you can always visit the website from ESO, ESO.org, where you will find hundreds of pictures and videos that you can use for whatever it is that you want to use them. And you can also find this 360-degree experience when you can walk through the different parts of the observatory at your own pace. And without nothing else to add, it was my pleasure to be your guide today, and I hope you have a pleasant afternoon.
Okay, thank you. Bye bye.